All right, so this is going to be chapter 4. It's going to be primarily talking about probability laws, probability rules, kind of sizing up for some things that we'll do more returning to kind of distributions. So we'll take a step away from thinking about, what the distribution of a data set looks like, talk more about probability, and then kind of combine that with stuff we talked about in chapter 3, means, variances, etc. So just to kind of set it up, when we're talking about probability, what are some of the things we're thinking about? So, just in, everyday speech, people would say something like, oh, what are the chances that sales decrease, right? Or what are the odds that a investment becomes profitable? Or what is the likelihood that this, new assembly method increases or decreases productivity? So all of these things are really talking about the same thing, which is, what is the probability? Like how, is this thing more or less likely to occur? Okay. So in order to kind of set up probability, we'll use a little bit of terminology. So we think about anything we're interested in the probability of. Even this is, what's the probability it rains today? We're going to have some experiment, right? So the experiment is going to be something we don't know what the outcome is going to be. I can't observe today's weather until it happens, right? So if I'm trying to predict tomorrow's weather, it's going to be some observation that I will have, but I don't know what the outcome is today. Excuse me. So this isn't kind of like the same as like an experiment in physics. This could be, like I said, anything. Is it going to rain tomorrow? Um, will I trip and fall down the stairs today? Anything that I'm not sure what the outcome is going to be. So when we think about probability, we're thinking about we have this experiment, and in theory, if we could run this experiment over and over and over and over and over, right, repeat it in the exact same way, we know that we could get different outcomes, right? So the experimental outcomes that we could see, if I only run the experiment once, let's say I roll, I've got a dice in my hand and you don't know what numbers are on it. So I roll it, you see there's a 6. Okay, that's one of the numbers on the dice. But if I only run it one time, I don't know what the other possible outcomes are. So I roll it again. Oh, this time, you tell me, oh, you rolled a 2. Okay, so now I know 2 is one of the possible outcomes. So as we repeat this experiment over and over, eventually we'll see all of the possible outcomes. Or if I think about, if I had a card deck, I don't know, you guys are from Indiana, so maybe this you already know. But for those of you that aren't, like let's say I wanted to play a game called Euchre. Well, it's not the complete card deck, and so you might not know which cards I pulled out, right? So Euchre decks, there's only what Jack, 9, 10, Jack, Queen, King, Ace. Um, so you know, you might not know that ahead of time. And if I only pull one card out of this deck, you're like, oh, okay, there's Jack of Diamonds in this deck. And then I run the experiment again. I pull a card at random. Oh, there's a 10 of hearts. Now, as I run this experiment over and over, eventually we'll get every single type of card and you'll see, okay, what are the possible experimental outcomes? If we only run this, um, you know, experiment a couple times, maybe my experimental outcomes are only that I see, a Jack of Diamonds, Ace of Spades, King of Hearts. If I only run it 3 times. The entire sample space would be every single possible outcome that I could see. So this would be eventually, if I pull enough cards, I will see every single outcome, right? Every single outcome, we would define that as the entire sample space. And then if we think about sometimes we might just be interested in a specific event, right? Or a subset of this sample space. So, if I'm thinking about a deck of cards, I would say, okay, what's the probability if I pull a card at random? What's the probability I get a king? Or what's the probability I get a queen or a king? Right? So that's only a small subset. Those are only a couple outcomes of all the possible outcomes. We would call that kind of our event that we're interested in. So, nice, easy visual. Remember this. Here's all of our possible experimental outcomes. Here's the ones that we saw from just our sample, right? It's, if we take a small sample, we might not see all of the outcomes. We might then be interested, okay, what's just a small kind of subset of that sample? That's our event. It's a little bit smaller, right? So all possible experimental outcomes, just what we see from our sample space, and then the event we're interested in. So some stupid examples I'll use just to kind of set us up initially with these probability rules is, flipping a coin. I can think about what are my experimental outcomes. I could get a heads or tails, right? I guess, I don't know, technically maybe it lands on its side, but I don't know the physics on that, if that's how possible that is. Um, I roll a die, unless I'm playing Dungeons and Dragons, right? I've got 1, 2, 3, 4, 5, and 6. If I choose a deck from a card, I already can use this one. I can see anything ace through king. If I'm not interested in suit. If I'm interested in suit, I just even have even more possible experimental outcomes. Playing a football game, win, lose, play a soccer game, win, lose, or tie. I guess technically in a football game, I should have put like playoff football game, you either win or you lose, right? There are ties in football. So um, these are just all different possible experiments, and we think about all the possible experimental outcomes. Okay. So the probability is going to be, if I carry out this experiment, what's the likelihood that I see a specific experimental outcome? Okay. So if I'm interested then the probability of an event, well, maybe my event, I said it's a subset of the sample space. Maybe it's not just, what's the probability if I pull a card at random from a deck of cards, I get a king. Maybe the event I'm interested in, what's the probability I get a king or a queen, right? So if we want the probability of an event, we will basically add up all the probabilities of every experimental outcome within that event. Okay. And this will get complicated here in a little bit, but for now, we'll kind of use that definition. So if I'm thinking about the probability of an event, right? Or an event, sorry. If I'm thinking about the probability of well, it is an event, but here specifically one experimental outcome. So we'll call that E. The probability that I see that an experimental outcome occur if I run this experiment, well, what's the lowest that probability could ever be? Well, if it can't happen, so let's say what's the probability I pull a card for, from a deck of cards and I get a 18 of clubs. Well, that can't happen. So the lowest probability we would say is 0, right? It can't be negative, right? Because at the very lowest, it just doesn't happen. And then what's the highest probability that it occurs? Well, let's say I had, a deck of cards and it was all aces. What's the probability if I pull a card, I get an ace? It's guaranteed. That probability, 100% chance I'll get an ace, probability is like the decimal form of percentages. So we'd say that highest possible probability I could ever see is 1. Now, usually, in most cases, we're going to see that it's somewhere in between 0 and 1. Right? But theoretically, it could be 0, could be 1. Right? And those are kind of the extreme points. Now, if I think about every single possible experimental outcome, they have to add up to 1. So just to kind of do some easy ones, if I flip a coin, the likelihood or the probability I get a heads, we kind of know is what? 50% or a probability of 0.5. So there's a 0.5 likelihood that I see heads, 0.5 likelihood I see tails. Those are the only two possible outcomes. Sure enough, when I add those up, they add up to 1. What if, I'm flipping, I think I've got an example here. Yeah, there we go. Just to kind of give us like some context, and I'll go back. What if I flip a coin twice? Oh, I could see heads, heads. I could see the heads and the tails, tails and the heads, 2 tails. Well, what's the probability I see 2 heads? 0.25. Probability to see a tail, 2 tails, 0.25. Heads then the tails, 0.25. Tails and the heads, 0.25. All the possible experimental outcomes, well, 0.25 plus 0.25 plus 0.25 plus 0.25, once again, add up to 1. So we know that these probabilities, if we add up for every single possible experimental outcome, right, they should add up to 1. Okay. We should start thinking about, you can compare this to some stuff we've already talked about. Kind of sounds similar to like relative frequencies, right? Those all added up to 1. So relative frequencies are actually kind of really are a probability, right? So there's different ways of assigning probabilities. So sometimes it's easy and we can use this classical method. So if it makes sense, like in flipping a coin, or if I'm rolling a 6-sided dice, like maybe it's the classical, I know everything's equally as likely, right? I can also use the empirical method, right? This is kind of when we're using our relative frequencies, and we'll talk about this here in a second, a little bit more in detail. And then the subjective method, sometimes we assign probabilities based off of experience, expertise. I can't run this experiment over and over. So if you think about something like, I don't know, yeah, the NFL draft or NBA, or whatever your sport is, right? Whatever the draft is, they don't know who's going to be chose first, second, third, but they based on experience and intuition and knowledge, they can say that this player has a more, higher probability of getting selected first than this other player. So the classical method, really don't have to spend a lot of time on this. Once again, this is just where everything is equally as likely, right? So every single every single experimental outcome has the exact same probability of occurring. I've already used this, flip a coin twice, I know that I have 4 different possible combinations I could see between those 2 coin flips. So each one has a probability of 1/4 of occurring. Once again, some of those probabilities should add up to 1, add 1/4 to itself 4 times, and yeah, we get 1. Okay. The empirical method is going to be something like, okay, I'm going to run this experiment over and over and over. So maybe I'm interested in what's I don't know, let's say I had a class of 60 students. It's a combination of the students I have this summer, right? And I'm interested in what their favorite kind of type of cuisine is, right? So I poll these students, I ask every single student, and based off of their responses, I have 15 of them chose that Mexican food was their favorite. Right? So my empirical probability that I assigned was 15 out of 60, right? So that's a probability of 0.25, or the probability if I chose a student at random that they like Mexican food would be 25%. So I'm collecting data, and then based off of that frequency, right, 15 that I see, I convert it into a relative frequency, and that's how I'll assign the probabilities. Now I kept it in percentage form here, but just like with relative frequencies, we can go from decimal to percentage form simply by multiplying by 100. So to be technically correct, this really shouldn't be a probability of 25%, but a probability of 0.25, or you can think about, whoops, about that representing 25%. Okay. So this is often probably the best way, is to assign probabilities empirically, like look at some actual outcomes when this experiment has been ran, and then use that data to then assign probabilities of what's going to happen in the future. But like I mentioned, sometimes we need a subjective method. So instead of, a draft example, let's say a company's going to hire a new CEO. I've got 4 candidates. Well, each candidate doesn't have an equal chance of getting the job. If, say, candidate Hill has already run, 2 businesses, Fortune 500 successfully, and Andy, has only ever worked as like a, I don't know, he's never been a CEO. He's just been a top level exec, but he hasn't actually been a CEO of a company. So based off of their different characteristics, people who kind of have knowledge in this industry say, well, it's more likely Hill's going to get the job than Andy, and et cetera, et cetera. Okay. Now that one's, once again, it's a little bit more, yeah, we don't often use it, right? We like to rely on that empirical kind of assignment of probabilities as much as we can. So, subjective method, welcome to probability and statistics. The classroom numbers are made up, or everything's made up, the numbers don't matter. So if you guys get this, if you haven't ever seen this, I'd try to drop some little interesting references, things I think you might want to see. You should go back and, like, I don't know, YouTube, Whose Line Is It Anyways? It's probably doesn't, not the most PC, might not hold up now, but it is a great show. So back to probability, right? So just some kind of notation, the way we're going to write things. We might be interested in the probability of different events. We also might be interested in the complement of an event. So the way we'll write this is A with a superscript C. So all the complement of an event means is it's anything other than that event occurring, right? So if this was, what's the probability I get a heads on a coin flip? That's my event A. A complement would be that I see a tails, any other outcome. More tricky. What if I had the probability if I pull a deck of card at random that I see a face card, right? A jack, queen, king, ace. What's that probability? Well, the complement of that would be that I see not jack, queen, king, or ace, but any of the other cards, right? 2 through 10. Okay. The union of 2 events is going to be anything that happens that's both in event A and in event B. So maybe if event A, let's say I'm interested in, what's a good one? So let's say event A is that if I pull a card at random, I see an ace, 2, or a 3. Event B, if I pull a card at random, I see an ace, king, or queen. What's the union of those 2 events? Well, it's any outcome that's in either one, right? It could be in A, could be in B, could be in both. So there it would be, the union of those 2 events would be what? Queen, king, ace, 2, 3. The intersection of events, right, is I have to have an outcome that's in both. So back to my previous example, what would the intersection of events A and B be? Well, the only card that was in both of those was an ace. So that would be the intersection of those 2 events. Now we write the union. I think it's easier to remember. You've got kind of this U shape to it. The intersection is kind of this upside down U. But someone told me once, let me see here. Someone told me once this is an easy way. I don't know. They said it's an easy way to remember it. So I'm thinking about like union B, right? That might be kind of easy to remember because here's like my union. Right? Now, usually the way we would say this, is it in A or is it in B? If I'm thinking about the intersection of those two events, it's this upside down U, kind of maybe feels weird. So this is going to be our intersection. This means that it's in either A, or sorry, it's in A and it's in B. Right? So someone said, maybe a good way, oh yeah, if it's upside down U, it kind of looks like, oh yeah, an A, right? This is if I'm looking for event A and B are occurring. If that is goofy and doesn't make sense to you, by all means, don't use it. I just had a couple students in the past tell me that, early in high school or someone, they saw that and it kind of helped make sense. So let's return here. Oh, actually, that's not what I wanted. There we go. Let me make sure you guys are seeing what I'm seeing. Okay, you are. So I've got the complement union intersection. We also have what we call conditionals, right? So this will it'll be a little bit easier to explain and make a little more sense when we talk about conditional probabilities. But for now, if I think about, event A occurring given that event B occurs, right? Well, let's go back to my kind of stupid card example. Let's say, I'm interested in the probability that if I pull a card at random, I see an ace, right? That's my event A I'm interested in. Well, and that's a, relatively low probability. There's a lot of other cards in the deck. But if you tell me that, okay, what's the probability? And actually, we'll even be more specific. What's the probability I get an ace of spades? That's my event A. Well, it's 1 out of 52 cards. That's my probability, right? However, if I tell you that event B has occurred, and event B is that when you pulled a deck of card or a card from a deck at random that you saw that you got an ace, and I tell you, okay, I draw a card, you can't see it, I look at it and I say, okay, it is an ace. Well, now what's the probability of event A occurring? Well, what's the likelihood now that there's an ace of spades? Well, if I've told you that there's an ace, right, event B has occurred, that's what I'm telling you, that I did pull an ace. Now, the probability it's an ace of spades instead of 1 out of 52 would be 1/4, right? So kind of this conditional is like we're getting some additional information. And often what that does is it limits kind of the potential experimental outcomes we could see. Before it was every single card. Now, once I tell you that I've pulled an ace, there's only 4 possible outcomes that could have occurred, right? I either got an ace of spades, ace of diamonds, ace of clubs, and I think I forgot ace of hearts, right? So we'll come up with some other better examples and just card examples, but I don't know. A lot of people know kind of deck of cards. It's kind of easy to explain that, kind of visualize that in our head. So just some visuals to go along with these different things, and not conditional probabilities yet. I'll kind of draw something out for you later that I think helps make a little more sense of those. But here, this entire rectangle is going to represent my every possible experimental outcome. I then might be interested in some of the outcomes, right? Those are in event A. And then here's some other outcomes I'm interested in. This would be event B. So the way visually we would kind of draw this is, well, here's the likelihood. I see something happening that's in event B, right? It's just this proportion of the overall experimental outcome space. And then you can think about, okay, what's the intersection of those two? Well, what outcomes are in both event A, but also in event B? So essentially, what really non-technical way to remember this is it's just where they overlap, right? That's the intersection. All the outcomes that are in either A or in B, or sorry, in either A and in also have to be in B. Now, the union of two events, it can be an outcome that's in either event, or it could be in both. So notice the union always includes the intersection because it's everything that's in A, but you can kind of think about here, but not in B. Right? Every outcome here is in event A, but it's not in B. Every outcome that's in event B, but not in A, but then also all of the outcomes that are in both. So the union will always include the intersection, okay? So we typically look at these probabilities, and a way we'll often do this is with what we call contingency table. So the way that this is set up is I've got both these two events, A and B. I then also have their complements, okay? And then I'm going to have a total column. So what these total columns represent, oops, sorry, is here's the probability. Sorry, let's start this over. these top 4 cells, what these represent are intersections, right? So here, the probability that I see an outcome occur that's both in A and in B, that probability is 0.4. The probability that I see something happen that's in event A, but not in B, right, or in B complement, that probability is 0.2. Okay? So if I think about, here, I'll go write this out because I don't think I have it in the slides. There we go. So if I'm thinking about, I know that the probability of A and the probability of B was 0.4. We then said the probability that I see A occur, but that the outcome is not in B, that was 0.2. Well, what's the probability that A occurs? If A occurs, it's either going to be A and B or A not in B. Those are the only two possible, right? The complement is every other thing that's not in event B. So really we can think about it as, if I add these two probabilities together, this is everything, every outcome that is in event A and also in B. So we want to visualize this here. Here's my event A. Here's my event B. Everything that's in A and in B, these would be all these outcomes. Well, where is B complement? B complement would be everything outside of circle B here. So if I take then this, add up the probability of everything that's in A and not in B, that would just be, I'll use a different color here, everything right here. So notice when I add those two spaces together, what do I get? Just the probability that A occurs. What does that look like on our contingency table? That looks like, oh, here's my probability of A and B plus the probability of A and not being in B. When I add across the rows, that's going to give me these totals, right? 0.4 plus 0.2 is 0.6, where these totals just represent the probability of the event occurring, right? So here, the probability of A occurring is 0.6. The probability A and B occur is 0.4. Probability that A and B doesn't occur, or B complement, is 0.2. I would do the same thing to the probability of A complement. So before I kind of show you event B, just notice if I wanted the probability of A complement, it should just be adding across the rows. So 0.1 plus 0.3. Sure enough, the probability of A complement is 0.4. And notice, hopefully, if I've done the math correct, the probability that A occurs plus the probability that A doesn't occur, well, that should always add up to 1. I think I've got a visual of that here in just a second, but kind of wanted to point that out right now. Now, if I think about event B, right, it's going to be a very similar thing, right? If the outcome is in event B, it's either in event B and in A, or it's in event B and it's not in A. Those are the only two possible scenarios, right? It's either, if it's in B, it's either in B and A, or it's in B and it's not in A complement. Or sorry, and it's not in A or A complement. So if I add up those two, right, add down the columns, essentially, it should give me those totals or the probability of the event themselves, just like adding across the rows, okay? So I'll give you just to be kind of comprehensive here, we could think about this would look like. So let's say I have this experimental outcome space. Here's A, here's B, right? So I would want everything that's both in event B and in event A. So this is the probability of A and B. And then where's A complement? Well, A complement would be everything that's not in A. Okay. So where does that overlap? So where's everything that's here? Everything that's in event B, but it's not in event A, that would be everything that's in event B, but not in A, so the intersection of B with A complement. Now, if I add these two together, that should give me the entire circle or just the probability of event B, okay? All right, so let's go back to the slides here. Actually, I'll do one more thing before we go back to the slides. Maybe, there we go. So let's say I had this entire experimental outcome space. I just want to point something out here. Let's say I had event A. If I think about what this entire experimental outcome space it represents, it will always be, well, it's every possible outcome. If I add up the probability of every outcome, we said that they should add up to 1. So we can always think of this experimental outcome space, this rectangle, is always having an area of 1. And then the probability of different events occurring, well, we know it has to be, even if the event was the entire space, it has to be 1 or lower. So if I know that this is the probability, represents the probability of A here, well then, the probability of A complement, I could think about, or where is A complement? It's going to be everything that's not an A. Notice these two things would represent the entire experimental outcome space. So we would say that if I take the probability of an event and I add the probability of its complement, they should always add up to 1. So we'll eventually talk about this being the complement rule, but I don't know. We're talking about complements and drawing different things. I think it kind of makes sense to bring that up here now as well. All right, so talked about these top 4 cells represent intersections. The totals represent the probability of the events themselves. Oops. I already mentioned, those top 4 cells all representing kind of intersections. So probably the A and B, probably the A complement and B complement. That's how we read these contingency tables. Now, a couple laws or rules we'll talk about. It doesn't matter how we say an intersection or a union. So if I say that something's in event A or it's in event B, that's the same as saying that it's in event B or it's in event A. I'm still talking about that same space. I could be, to be less technical, in either circle here. Now, if I want the intersection, I can, once again, doesn't matter the order in which I say it. I could say I want the probability that I'm in A and in B, or I could say the probability that I'm in B and in A. I'm still talking about that same space where they overlap. Okay. So I don't know, kind of stupid way to always, think about intersections, right? When you say it's fine, when it's actually fine, very small intersection, right? Very, very, very small occurrence when that actually is true. Now, this is what I already kind of showed you, just in a slightly different way, right? So if I take the likelihood or the probability that I'm in event A, and I add that to A complement, it's the entire space of 1. So notice, how do I get that complement rule then? If I can get my mouse to work, there we go. How do I get that complement rule? Well, if I've got the probability of A plus its complement has to be the entire experimental outcome space, all I'm going to do is rearrange this a little bit. So I have the probability of A complement. I just subtract this probability from both sides. And I get that the probability of a complement is just 1 minus the probability of an event. Right? Or if I know the complement, I could kind of do vice versa, right? I know that the probability of A would have to then be 1 minus the probability of A complement. Excuse me. So this idea is where that complement rule comes from. We'll go back to the slides here. Okay. So, keep forgetting to click on that. The addition rule is going to be a little bit different. So I kind of mentioned earlier, the union, right? Everything that's in either one of these circles always includes what's in both circles as well, or includes the intersection. So if I want to find the probability of the union, what I could do is, well, I could take everything that's in event A and I add that to everything that's in event B. So if I add up the probability of A and B, does that give me the union? Well, not quite, because I double counted every outcome that's in both in A and in B. So I can find the union by adding up the probability of A, adding up the probability of B, but I then have to subtract out the intersection because I double counted it. So I'll subtract it out once. That way I've only counted it 1 time. Okay. Let me see here. Yeah. Now another way of thinking about this gets the same result, but if I want everything that's in A, oh, come on. This mouse is so finicky. So if I want everything that's in A, but not in the intersection, so that would be the probability of A minus the intersection. That represents the probability of A. If I want everything in this kind of half moon thing over here, that's everything that's in B, but not the intersection. And it would then, okay, I've got this kind of crescent moon, this crescent moon. What's the only piece left from the union? Well, that would just be the intersection. Notice if I write it out this way, these would cancel, and I still have that the union of two events, probably in A or B, is the probability of A plus the probability of B minus that intersection. So just a different way of kind of thinking about this. We could really complicate this a little bit, but I think it's worth kind of mentioning just to be complete here. When I'm thinking about the union of two events, I could also, and this isn't really going to be as, what's the right word, useful in terms of like applying this to problems and things like that, but I think it's useful in understanding the concept and also kind of reiterating some of the things we've talked about. So if I have A here and B here, this is going to represent everything that's in circle A and not in B. Okay. Here's going to represent everything that's in circle B, but notice it's also not an A. Okay. And then have kind of the third area here. I add each up one of these up. This is the probability I'm in A and I'm in B. So another way I could think about writing the union is it's the probability I'm in A, but not in B, the probability that I'm in B, but not in circle A, plus the probability that I'm in both of them, right? That would kind of represent these three different areas. So just a different way of writing that. Now, why might this be useful? Well, if I'm looking at a contingency table, I should have these three values. Right? So I think I'll hit up on this on an example later on, but just wanted to show you for right now a slightly different way of thinking about that union, kind of breaking it down into those three areas. I don't want to stop video. I want to go back here. Okay. So visually on a contingency table, how could I find the union of two events? Well, I could take the probability of A plus the probability of A is 0.6, probability of B is 0.5, and then what's the intersection? 0.4, so 0.6 plus 0.5 minus 0.4 gives me 0.7. Notice it's also the sum of these three. Now I'll explain why here in a second. But this is a non-technical way of remembering it. If you ever want the union of two events, just go to the intersection on the contingency table, make like an L, right? Just go over and down here, or if I was here, I'd just go over and up, right? And add those three together. So 0.2 plus 0.4 plus 0.1, excuse me, sure enough, gives me that same value of 0.7. Why does that work? Well, what do these areas represent? Here, I've got the probability of A and B. Here's the probability of A and B complement. Here's the probability of B and A complement. Notice that was the alternative way of writing that union of two events. So I could find each of these three values from my contingency table, probability of A and B, A and not B, B and not A. Sorry for the delay. That was just these three cells here. Right? So just different way of kind of doing the same thing. Right? Let me think if there's anything else I want to say here. It should be good. If I quit making that beeping noise, there we go. Some other things we'll talk about when we're looking at contingency tables or thinking about intersections or unions of events are two events mutually exclusive? Okay. So we would say two events are mutually exclusive if the intersection of those two events is equal to 0. So the idea of being mutually exclusive means they can't happen at the same time. So, let's say, I don't know, what's the probability that I pull a card from a deck of cards? What's the probability I get a 10? What's the probability of the 10 and I get a jack. Well, if I'm only pulling the card one time, I can only see one of those things occur, right? What's the probability I see, this happen or this happen? They're mutually exclusive. So that kind of is nice because now when I'm looking for the union, and I might have said that backwards, sorry. When I was thinking about my example where I pulled a card from a deck of cards, what's the probability I get an A? What's the probability I get a 10 is event A? What's the probability I get a jack? That's event B. Well, what's the probability I pick one card, I get a 10 and a jack? It's impossible. I can only see one of those happen, so we would say they're mutually exclusive, which means the union of two events, right? If those two events are mutually exclusive, it's just adding up the probability of each event occurring because that intersection is 0. So now when I'm using my addition rule, I'll take the probability of A plus the probability of B, but there is no thing I didn't double count anything, right? So I don't need to subtract that intersection again. And even if I did, I'd be subtracting the value of 0, so I can kind of just ignore that. Right? Now, what would that have to look like in a contingency table? I'd have to have that the intersection of these two events is 0. Okay. All right. So another way of kind of thinking about this visually, if I'm drawing out the circles, they don't overlap, right? So think about things that are mutually exclusive, right? If you guys are old enough now, you don't remember, but phone internet access were mutually exclusive in the 90s. If you were on the internet, you couldn't be using the phone at the same time. Trust me, I got in plenty of trouble with my parents for being on and the internet too much and missing phone calls, right? Another law that we'll talk about, it doesn't necessarily have a specific name, but it relates to when we're working with these contingency tables, is that if I think about what this blue area represents, I'll kind of give you a better visual of this. It's going to be the intersection of the complement of the two events. So why is that the case? Okay. So if I've got my entire experimental outcome space, I've got event A, and I've got event B. Excuse me, where would red marker that might show up? Oh, I had another red marker. I do. So if I think about what's not in event B, that's what it's dying to. So this red area here would kind of represent B complement, right? Everything that's not in B. Everything that's not in A would be this area here. Well, it's kind of hard to see maybe, but like here, there's only blue, there's only red. The places where there's blue and red are only the space outside each of the circles. Well, if it's in the blue area and the red area, what that really represents is the probability that it's in A complement and B complement. So if I take the union of two events and I then add to that the intersection of the complements, notice that fills up the entire experimental outcome space. So if I take the probability of the union of two events, I add that to the probability of its complements, those should add up to 1. I can rewrite the union of two events as the probability of each event occurring, probability A and probability B, and then subtracting out what I double counted, the intersection. So this equation, these 4 components should add up to 1 as well. Okay. And we'll kind of play around with this when we actually look at contingency tables, thinking about what this looks like in practice. Right now, I'm just kind of setting us up. Oh, sorry. All right. So just a little bit of work with these contingency tables, just to kind of put some of these rules and laws into practice before we start kind of making them a little more complicated. Let's say I gave you some information like this. Right? How could I find the probability of B? Okay. Well, it's a couple different ways I could do this. So the first way might be, I don't know, just like using formulas, maybe not quite as critical thinking, but it's okay. We'll start with it. Well, let's say I look at this. I'm like, okay, I know that whatever this probability of the union is, right? It's either A or B, and I add to that the intersection of the complements, that's the entire space of one. So I could use these three components, use this equation I had from before, plug in the probability of A, plug in the intersection of the two events, plug in the intersection of the complements, and then just a little bit of math, right? So if I'm looking at these values, I got the probability of A 0.5, intersection is intersection is 0.1, intersection of the complements is 0.3. What I'm thinking about there is, I know that this equation will hold. So the probability of A plus the probability of B minus the intersection that represented the union of those two events, right? The area and the circles. But then to fill out the entire experimental outcome space, I also had to add in that kind of light blue shaded area. Well, I just grab the values now. So I've got 1 is equal to, I was told the probability of A is 0.5. I don't know the probability of B. Complement, or the intersection of the two events is 0.1. Intersection of the complements is 0.3. Now it's just a little bit of algebra, right? So what, 0.8, 0.7. So 1 minus 0.7 should be the probability of B. So I just added these up. I got 0.7. I subtracted 0.7 from both sides. I now know the probability of B is 3. Okay. Now, another way of thinking about this is if I looked at that very quickly, and I could kind of see this. So maybe I look at that visual and very quickly I say, okay, look, I know that the entire area outside of these two circles, that just that's 0.3. I know that if I add that area plus the area in the circles, that has to add up to 1. I know the area in the circles has to be 0.7. So I know that the area in the circles is 0.7. Well, what is that area in the circles? That's just my union, right? How do I find the probability of a union? That's just the probability of A plus the probability of B minus the probability of the intersection, because I double counted it. Well, I said what area has to be in those circles, looking at what has to be 0.7. I know probability of A is 0.5. Probability of the intersection is B. Once again, now it's just a little bit of math. Okay, 0.5 minus 0.1, so 0.4, so minus 0.4 from both sides. And I'm left with the exact same thing, just that the probability of B is 0.3. Okay. So just different ways of thinking about doing the same thing. But both lead us to the same final answer, right? Excuse me. All right. So I think I'll end this video just to kind of make them a little bit smaller. These are our basic probability rules. I've got one more rule, which I think is a little bit more complicated, which is looking at conditional probabilities. So we'll kind of make a separate video where we start with that. And then one where we look at how do we do this in Excel? How do I build these contingency tables and then start to answer questions about probabilities in Excel?